Hokie dokie. Welcome to the Math 1014 Exam 1 review session. This is for obviously 1014 students, not 1524, 1025, 1026, whatever. All right. If you want access to 1524, 1025, or 1026 sessions, I encourage you to become a member of the You Will Get an A option. That's the second option of memberships stuff on my channel, yada yada. I already have all sorts of pre-recorded sessions for those courses, and I have not done the 1014 stuff, so that's what we are getting into today. So let's shrink me down, let's blow this up, and we're essentially just going to get right into it. Let me get this right. Okay, let me check this is good. Check the sound and whatnot. Check the sound and whatnot. Sounds pretty good. All right, so we're going to get right into it. Good morning. Welcome to Math 1014 Exam 1 review session. I'll go ahead and write it here. Math 1014 Test 1 or Exam 1 review session. Today we are going to get into 18 problems, 18 practice problems that you could potentially see on your exam, or at least like it's going to be content that's in the same realm. It's the same material that might be on your exam. I'm not sure if your exam is specifically through the MPO or if it's written by the teachers now. It's all different now, so I'm making do with what I have. So review session. All right. So what I have is 18 different practice problems to mimic what would have been the Math Emporium exam that would have 18 questions. 18 questions that come from the practice problem system from quizzes 2 and 3. All right, let's jump right into it. Problem 1. They ask which of the graphs below represents a function. So for this problem, we want to use the vertical line test. So we are using the vertical line test, and the idea is as we scan across with this vertical line, if there are any two or more points that lie on the same vertical line, then that graph does not represent a function. So as we scan through graph A, we see that these 2 points lie on the same vertical line. Therefore, for a single input, it has created 2 outputs. That's the problem. That's why it's not a function. And so graph A is not a function. As we scan through graph B, it looks good, looks good, looks good, all the way until the end where we see those 2 dots lying on the same vertical line. So it turns out that B is not a function either. So neither is a function. And that's it. So if there's just a single dot on every vertical line, then that would be a function. If there's 2 or more dots on a vertical line, that fails the vertical line test, so that graph would not be a function. Let's get into problem number 2. It says the student's grade depends on the teacher's satisfaction in a manner symbolized by G, and we're finding the equation that represents that. Okay, so the way I approach this is identify the 2 variables that they're talking about. So we have the student's grade, and then we have the teacher's satisfaction, and then we have this sort of connector word between those, which I will call depends on. So the phrase depends on is this connector phrase between the student's grade and the teacher's satisfaction. So the way I approach this is thinking about it in terms of cause and effect. Cause and effect. Which of these 2 variables causes the other? Like, what's the cause, what's the effect? What's the input and what's the output? It says the student's grade depends on the teacher's satisfaction. And so it's the teacher's satisfaction that is affecting the student's grade. So teacher satisfaction comes first. That is the cause. And the effect is the student's grade as a result, right? And so the cause is like the input, and the effect is like the output. And so what I look for is for the input to be inside parentheses when we're scanning through these equations here. So I want to see teacher satisfaction, or maybe just satisfaction. How do they word it? They say teacher satisfaction. So we look for teacher satisfaction inside the parentheses. And then, so that allows us to eliminate A and B. And then we want to see the student's grade, the effect, as the output. We want to see it on the opposite side of the equation. And so just grade is what we're looking for. Success doesn't make any sense. So we eliminate D and go with C. So just get comfortable with these. If you haven't seen these yet or don't feel good about these, just practice like identifying the cause and effect, the input or output, and then getting comfortable with the connector words, because sometimes it says depends on, sometimes it's influences, sometimes it's influenced by, and so it's all a little different. So just think about it in terms of cause and effect. All right. Sorry, trying to get my hair straight. Number 3. They say define f and g by f of t equals x and g of x equals t. Use the table below which of the following is correct. So we're trying to identify whether f and g are functions. Starting with f. The quick way to identify if f is a function is to identify its input variable. The input variable is t because t is inside the parentheses. So we want to see if this input variable t is repeated ever. So when we look at the t values, we scan across the t values, we ask ourselves, are there any t values that are repeated? So we have -10, -1, -13, -6, -11, and so on, yada yada. I do not see any t values that are repeated. So f should be a function. If there were any t values that were repeated, then f would not be a function. So f checks out. Now we check function g. We identify its input. Its input is x. And so what we're going to look for is, are any of the x values repeated? Do any of the x values repeat? Because if they do, then g will not be a function. So when we scan through, we see a 7, -6, 14, 16, 7, which we already saw at the start. There's 2 7s. There are 2 x's of 7s, meaning if you input a 7, you could either get an output of -10 or you could get an output of -11. And that's an issue. You can't have one input producing 2 outputs. That's the problem. That's why it's not a function. That's why we look for 2 repeated input values. So because we see 2 inputs that are repeated, g is not a function, but f would be a function. So only f is a function. Option D is our answer, and we keep it going. Okay. All right, number 4. Given this function, a value not in the domain of f is what? All right, I'll go ahead and say a quick way of going about this is we are trying to find the x value that makes this denominator equal to 0. Like if we were to plug these x values into that denominator, which one makes the denominator equal to 0? That's one method of going about it, and really that's essentially what we're looking for. But the approach I take is setting the denominator equal to 0, factoring it, and then getting the x values from that. So the reason we're trying to find the x values that make the denominator equal to 0 is because when a denominator is equal to 0, like say we just have some constant c divided by 0, anything divided by 0 is undefined. And so if we're looking for an x value that's not in the domain, any x value that makes the denominator equal to 0, when plugged into the function, would make the denominator equal to 0, which would make the whole function value undefined. So that's why the x value would not be in the domain, because the domain is only the set of x values that, when plugged into the function, produce defined function values, not undefined function values. Okay. Anyway, so set the denominator equal to 0, factor it, So what two numbers multiply to -9 but add to 0, essentially? This is really just a difference of two squares. So this is our plus and minus situation. And then square root of 9 is 3. So plus and minus 3. And then from each of these factors, we set them equal to 0. Solve for x, we get -3 and +3. And so, which one of these answers do we see? We see +3. And that's it. So, both -3 and 3 are values that are not in the domain, but we just picked the one that they have. Okay? Okay. Enough on that one. Let's go to number 5. They say find the domain of this function here. So this function, notice there's no denominator, so there's no chance of a denominator equaling 0, but there is a square root. And what values can we not have underneath a square root? Can we have positives? Yeah. Can we have 0? Yeah, that's fine. Can we have negative numbers? No. So the way we find our domain or our domain restrictions is by taking everything that's underneath the square root, and because everything underneath the square root cannot be negative, that means it has to either be positive or equal to 0. So it has to be greater than or equal to 0. So we set the inside of whatever's underneath the square root greater than or equal to 0, and then we just solve for x. So let's add 10 to both sides. We get -2x is greater than or equal to 10. We divide by -2, and when we divide by a negative, when dealing with inequalities, the sign flips. 10 divided by -2 would be -5. So we have x is less than or equal to -5, and that already is our domain. D is our answer, and we're done. So for square roots, just set the inside of the square root greater than or equal to 0 and solve for x. That was number 5. Here is number 6. They say assuming that the ends of the graph extend, which of the following values is not in the range of the function? So the range is really just the set of output values by the function. In other words, the set of y values that are produced by the function. So which of these values is not in the range? Well, if we see that the function has a lowest y value of 1 and then it just goes up forever, then it's not hitting any y values that are less than 1. So a value that is not in the range would be a value that is less than 1. And it turns out that 2 is greater than 1, 11 halves greater than 1, 7 halves greater than 1. So all of these other 3 values are in the range. They are produced by the function. They are some output of that function. But -1/2 is not produced by that function. -1/2 is down here. And that function does not ever go down there. Okay? That was number 6. Here is number 7. They say we have a bacteria culture being examined and it's growing in some laboratory. During the first 2 days, the culture count increases from this value to this value. And then there's some contaminant, and then the bacteria only increases by 593 over the next 4 days. Then they ask, what is the average rate of increase of the bacteria count per day for the entire observation period? I'll go ahead and say that average rate of increase or average rate of change is just a fancy phrase for the slope. Whenever you see average rate of change, that just means slope. So if they're asking for the average rate of increase, we need to find the slope between what 2 points? Well, let's find out. They want to know what the slope is over the entire observation period. So basically from time 0 to whatever the time value is at the very end. Well, how much time has gone by over the entire observation period? They say 2 days have gone by, right? But then an additional 4 days have gone by. 2 plus 4 is 6. So the entire observation period is 6 days. So you'll see what I'm doing is constructing 2 ordered pairs of the form t comma, I guess like population or culture count, whatever. And so we want to know what's the culture count at the start, what's the culture count at the end of the 6 days. So at the very, very start, they tell us during the first 2 days, it increases from this to that. So the 7871 is the starting value. It's the starting culture count, starting Y value, whatever. It increased to 9,130 over the first 2 days. But then after that, it also increased by 593. So whatever the result of adding these two values is, would be our ending culture count, like our final population, I guess. So we will calculate that. Let's do that in Siri. 9130 plus 593.
It's 9,723.
9,723. All right, very good. So now that we have two ordered pairs, again, we're finding the slope. So we find the slope by doing y2 minus y1 over x2 minus x1. 9,723 minus 7871.
Whose contact info are you looking for?
We broke the system. Okay, nope, not doing that. Let's get, I'll just use Desmos. Let's see. Nine, 7, 2, 3, 78, 71. All right, so we got 1852. And we're dividing by 6. 1852 divided by 6.
The answer is approximately 308.6666.
All right, very good. So approximately 308 or 309, 308.7, that works. And that is the slope. In other words, the average rate of increase over the entire observation period. Okay, that was number 7. Here is number 8. They say determine the values of m and b for the linear function. So the idea is they've given us a function that looks a little jumbled, or it's got a lot of terms, and our goal is to simplify it, combine like terms, and eventually have it in the form of f of x equals mx plus b. Okay, so let's start by distributing the 2. 2 times 4 is 8. 2 times negative 6x is negative 12x. We still have the minus 7 over 2x plus 3 over 2. So we are just simplifying this here. So our like terms are the minus 12x and the minus 7 over 2x. I might start with those. So I'll just leave the 8 for now. We want to make sure if our answers are in fractions, so I'll just do it by hand. I'm going to convert the minus 12 into a fraction that has a common denominator with the other fraction. So if the denominator over here is 2, how do we convert 12 to have a denominator of 2? Well, you think about what divided by 2 gives you 12. 24. You could also think about it as like if it was originally 12 over 1, you're converting it to something over 2. 1 times 2 is 2, so 12 times 2 is 24. However it works, however you want to do it, whatever. However it helps, I guess. So we have gotten it to a point where we can combine the x terms. This has an x, sorry. Negative 24 minus 7 would give us negative 31x over 2, or 31 over 2x. And then we still have the 8 and the 3 halves. So we could think about the 8 as 16 over 2. Do the same sort of conversion. If it was 8 over 1 and we need it to have a denominator of 2, we multiply the 8 by 2 and the 1 by 2 to get 16 over 2 plus 3 over 2. So the 8 went to this, and 3 halves is right there. Okay, 16 plus 3 is 19. We leave it over 2, and we still have the minus 31 over 2, or negative 31 over 2. X. So what we have is mx plus b. So the m is negative 31 over 2, and the b is 19 over 2. All right. That was number 8. Let's do number 9. Here they say all the graphs appear to be straight lines, but using the 3 points, show on the graph which one could represent a linear function. So what we need to do is check if the slope between points 1 and 2 is equal to the slope between points 2 and 3. If the slope is consistent from like one segment to the other segment, if the slope is the same, then that will kind of prove we have a linear function. A linear function, or a line on a graph, should have a constant slope or constant rate of change the entire time. So the way I go about this is just by analyzing the rise over run, instead of having to do like a y2 minus y1 over x2 minus x1. If you want, you can do that. You can identify the ordered pairs for each point and find the slope using slope formula. But again, I prefer just rise over run. So I will do that for these. So from 27 to 37, we have risen 10. And from 6 to 8, we have run 2. So 10 over 2, that's rise over run. That is equal to 5. So now we find the slope in a similar manner between these 2 points. So we rise from 37 to 43. That is a rise of 6. And we run from 8 to 9 by 1. So 6 over 1, does 5 equal 6 over 1? In other words, does 5 equal 6? 5 does not equal 6. So A is not our linear function. Let's do B. Let's do the rest of them. All right. We rise from 7 to 10. And then we run 6 to 8. So we run 2. Next, from this point to this point, we rise 2 and run 1. So we have 2 over 1. Does 3 halves equal 2 over 1? It does not. All right. From 21 to 27, that's a rise of 6. From 6 to 8, run of 2. From 27 to 30, that's a rise of 3. And 8 to 9, that's a run of 1. So my question is, does 6 over 2 equal 3 over 1? Yes. They're both equal to 3. And so C would be our answer here, because the slope between points 1 and 2 is equal to the slope between points 2 and 3. Okay? Okay. No questions? Very good. Okay. I got 4 viewers. That's fun. Hope y'all are enjoying this. Hopefully you have no questions, but feel free to ask questions. If y'all are watching, why not? All right. So, according to somebody's law, the resistance to flow in a blood vessel, R, is directly proportional to the length L of the vessel and inversely proportional to the 4th power of the radius R of the vessel. Very wordy. Let's talk about what to focus on. They're giving us information about R and what it is proportional to the other things, or how it is proportional to these other variables, I guess. So the goal is to write an equation for R. What is R equal to? Well, if they tell us that R is directly proportional to the length, L, that means we can write R as the product of some constant K times L. But R is also inversely proportional to the 4th power of the radius R. The 4th power of the radius R would be R to the 4th. And so, to be inversely proportional means that capital R should have the relationship of like K divided by the 4th power of R. So the main idea is, if it says something is directly proportional to that thing, you should see that thing in the numerator. If it says it's inversely proportional to something else, you should see that term in the denominator. So inversely goes in the denominator, directly proportional numerator. Okay, and so we've sort of combined the two things they told us about R. So we put L in the numerator, R to the 4th in the denominator, with just a single constant of K. Now, R equals this, L equals this, radius equals that. So the goal is to plug in those values accordingly. So capital R is 182.4 equal to K times L, which is 13, over R to the fourth, where R, the radius, the lowercase r, the radius is 0.4. That's being raised to the fourth. So the goal is we plug these values in, and the only unknown is K, so we have to solve for K. So how do we solve for K? How do we get K by itself? Well, the quick way would be to multiply by the reciprocal of what we see here. So multiply by 0.4 to the fourth and divide by 13. You, of course, could calculate this first and then divide by that in the end. I'm just going to kind of somewhat simplify the process. I don't know. Simplify is a weird word for it, but it's just efficient in my head. So we multiply by 0.4 to the fourth because that cancels that, and then we divide by 13 because that cancels that. So it leaves us with K on this side. And so as long as we can calculate this, we'll be good. So let's try that in Siri. Ready? 0.4 to the fourth power divided by 13.
It's approximately 0.0256.
Fair enough. I was not quick enough. So we have that times 182.4. Let's try it again. 0.0256 divided by 13 times 182.4.
That would be approximately 0.3591.
All right, so 359. 0.359. We'll go ahead and tack on the 1. Why not? This is our K value. We're not done, but that was our first step. So what they next they ask, what is R when the radius is 0.5 but the length is unchanged? So now the idea is we're going to restart with this equation. We're going to find whatever capital R is when the radius, the lowercase r, is 0.5, still being raised to the fourth, and the length is unchanged. The length before was 13. They told us that, so we just plug in 13 for L. And now we actually know what K is. So we just plug in K wherever K is supposed to be. So we have 0.3591 times 13 over 0.5 to the fourth. All right, so let's try this in Siri. 0.3591 times 13 divided by 0.5 to the fourth.
It's 74.6928.
I'll take it. 74.69. All right, that should do it. So about 74.7, that's option D. And that's it. So construct the R equation. I want to say for this one, the R equation is always the same. Like it's always KL over R to the fourth. I could be wrong though. And then plug in the R, L, and lowercase r values. Solve for K. Reset. Plug in that K with the length and the new radius to get your new capital R. Okay? Okay. That was number 10. Here's number 11. Sorry, I'm like kind of tweaking off coffee right now. I don't know what's going on. I feel crazy. All right. Drink some water. All right. They say the population of departments in a particular company are given in the table below. Use the Hamilton method to apportion 25 IT technicians to support all of the departments. So the idea here is they're giving us a chart with departments and populations, and what we need to like gather from that table is ratios. We need to understand, like, if we take the total population and we think about like which department, I guess like we think about which, what am I trying to say? We think about the ratio that each department holds, what percentage of the total population each department is like taking up. We need to like keep that in mind when we're trying to apportion the 25 IT technicians to these departments. Like some departments might need more based on their higher population, some might need less based on their lower population, etc. So here's how we do that. We start by finding the total. let's find the total. We need to know the total population. So we add the population values. 32 plus 24 plus 25 plus 45 plus 22.
That would be 148.
All right. So we have 148. Now we need to figure out the actual ratios for each of them. And what I'm going to do is find the ratio by doing 32 divided by 148, 24 divided by 148, 25 divided by 148, and so on. That's going to give us the ratio of the population that each department takes up. But to save time, I'm going to also simultaneously multiply each of those ratios by the 25 IT technicians. So I'm going to find the ratio by doing, say, 32 divided by 148. Then I'm going to multiply it by 25. And that should start to give us the values that we're actually looking for in the chart here. So let's get started. 32 divided by 148 times 25.
It's approximately 5.4054.
So I'll call that 5.4. Let's do the next one. 24 divided by 148 times 25.
It's approximately 4.054.
So 4.05. So that was the second one. And now 25 divided by 148. So 25 divided by 148 times 25.
It's approximately 4.2229.
All right, so about 4.22. Now, Department D, 45 divided by 148 times 25.
It's approximately 7.6013.
So about 7.6. Last one, Department E, 22 divided by 148 times 25.
That would be approximately 3.7162.
So about 3.72. Now, these are the values we're basically looking for, but obviously some of these require some rounding. So the idea is to find the sort of like closest chart to what we have here for A through E. So I would assume like something like B would definitely be 4 still. C would probably be 4. Just that alone leaves us with option D, and let's see if it makes sense. This kind of rounds down to 5. This probably rounds up to 8. This rounds up to 4, and that's perfect. That's option D. So again, find the total, find the ratios for each department, and then multiply them by however many IT technicians you have, and then just think about the rounding up or down accordingly, and find the closest chart to that. All right, that was 11. Here's number 12. All right, no questions. Beautiful. Still got people. Still got 4 viewers. That's great. Thanks for sticking around. We're finding the arithmetic and geometric means of the following list of numbers. So we have 7, 11, and 9. The arithmetic mean is really just the regular mean that you're used to, most likely. So to find the mean or find the average, to find the arithmetic mean, what we do is add up all the values and we divide by however many values there are. So 3. And so 7 plus 11 plus 9, that should be 27. Yeah. Divided by 3, that gives us a nice value of 9. So arithmetic mean should be 9. With that, we can eliminate a handful of answers. All right. Now, geometric mean, something a little less used to. Let's see. Can you go over simplify radicals? Sorry, there's like a heart blocking your question here. All right. Can you go over simplifying radicals x? Oh my gosh, there's like emoji thing. All right, this is killing me. Let me see if I can see it. And all right, there we go. Simplifying radical x equation, but as a fraction. Okay. Yeah, I'll see if I can talk about that right after this question. Okay. So geometric mean. We'll go ahead and knock this one out. Geometric mean is similar, but instead of adding and dividing, what we're going to do is multiply and then take some sort of square root. So instead of adding up all the numbers, we're going to multiply all the numbers. So 7 times 11 times 9. And then instead of dividing by 3, we still want to incorporate the 3, but we want to actually take the cube root. So because there are 3 numbers, we take the cube root of that entire product. If there were 4 numbers, we would take the 4th root of that entire product. I also want to point out, taking the cube root is the same as multiplying all these and then raising it to the 1/3 power. So the cube root is the same as a 1/3 exponent. So let's go and do this in Desmos. 7 times 11 times 9 raised to the power of 1/3. So we get 8.85. For our geometric mean. So for geometric, you multiply them up and then take whatever root based on the number of values you have. Okay, so 8.85, that is option D, and we're done. All right, so back to Adrian. You said, can you go over simplifying radical x equation but as a fraction? So I wonder if you could give me an example. Let's see. So radical x equation. So we have something like this, but you said as a fraction. So simplifying. Can you go over simplifying radical x but as a fraction? Maybe, I don't know if this is right, but do you mean like how you can rewrite a radical x, like square root of x, as x to the 1/2? Because that can be translated to a 1/2 like that fraction. But I feel like that's not what you're looking for. Maybe something with like where you have numbers like this, or one of the questions where x is greater than 0. Okay. Okay, I'm assuming it's in here somewhere. Let me see if I have any game on that. Let's see, x greater than 0, radical expressions. Yeah, I'm a little lost, I'll be honest. Radical expressions, maybe something like that. Here, let's see. Sounds good. While you're doing that, just for time's sake, I'm going to go ahead and keep working through here. But definitely let me know when you find something like it, even in like the problem type or 151A. That was quick. You crushed it. Okay. Let me see. I have to scroll through my phone real quick. That'll be a little easier, to be honest. Because I have these pictures somewhere else. You know, I'm going to look it up in my videos. That might actually be, it's going to be silly, but actually would be faster. Let's see, videos 151A 1014. Beautiful. Okay, still don't even know which one this is. Chick-fil-A. Okay. Oh, something tells me that this is maybe not what you're talking about, but you said 151A, right? Yeah. Are you talking about the average rate of change one? Like this one? If you can, actually try to send me a go ahead and send me an email. Oh crap, with those 1524. That's all right. No, this is 1014. But let me try to send you something on that. Let me see what's popping with that. 151A 1524. Let's see. Oh, that's one. Okay, one of the crazy ones. Yep. Okay. Well, I might just link you to this for now, but you know, watch these videos. This will help you out. Here, let me get a little link going here. That's all. No, you're good. You're good. I'm glad we sorted that out. But you're welcome. All right, I'm gonna get back to this. But if you have any other questions on that stuff, definitely, you know, comment on my videos or send me an email or whatever. My email is carterdeeemath carterdeeemath@gmail.com. Don't be afraid to ask questions. All right. So number 13 on this one. They say when the rational function is completely reduced, what is the degree of the polynomial in the denominator? So when the rational function is completely reduced, what we are trying to do here is simplify this radical expression, this rational function as much as possible. And so to simplify it, the first thing to look for is any quadratic expression like this. We want to simplify by factoring any quadratic expression like that. So to factor, we are looking for two numbers that multiply to -12 but add to +4. And so we think about 6 and 2. 6 and 2, if we have a +6 and a -2, 6 and -2 would multiply to -12, but they would add to +4. 6 minus 2 is 4. So then we have the rest of the denominator here. And so next we want to think about, after we factored, does anything simplify? So on top and bottom, we have x minus 2 and x minus 2. Let me find my little camera here. There we go. All right, so on top and bottom, we have x minus 2, right? So we can eliminate one x minus 2 and one of these x minus 2s. Keep in mind, we have x minus 2 squared. So we really have like x minus 2 times x minus 2. So we get rid of one of them, leaving us with just x minus 2, okay? So we canceled out one of the two, but we still have one on the bottom, okay? So now, they ask, keep in mind, what is the degree of the polynomial in the denominator? So if this is as simplified as we can get, we now want to think about what would happen if we expanded this denominator, if we multiplied it out. Well, we'd have one x term, and we'd have this x term being squared. Like if we expanded everything out, in terms of the x terms, we'd have an x times an x squared. X times x squared is x cubed. And that, that has that has an exponent of 3, and so the highest exponent in the denominator, in other words, the degree, would be 3. So I didn't clarify the degree. The degree of the polynomial is the highest exponent of the x terms in that expression. And so the degree of the polynomial, the highest exponent is 3. Because when we multiply this out, we have an exponent of 3. Okay. That was 13. Here is number 14. Given the piecewise function, find the value of g of -3. So -3 is our input. To find g of -3 means we are plugging -3 into the function and trying to find the y value, trying to find the g value. So here's how it works with piecewise functions. We're plugging in -3, so do we plug it in here or do we plug it in here? Well, we want to look at the domains, these intervals of x values here, and ask ourselves, does -3 fit into the first inequality or the second inequality? In other words, like if -3 took the place of x here, and we ask ourselves, is -3 less than or equal to 10, or is -3 greater than 10? -3 is definitely less than or equal to 10. So because it fit into this interval or this domain, we need to plug it into this piece of the function. So we plug in -3 to that piece because -3 fit into that piece's corresponding interval, corresponding domain. And we just evaluate this. So -7 times -3 is 21 minus 6, that is 15. And we're done. So for finding g of whatever, or plugging in some x value into some piecewise function, figure out which interval or domain the x value fits into, and then just plug it into that corresponding piece. Okay. All right. This is problem 14. Sorry, this is problem 15. And they ask, for this function, the set of all x values not in the domain of f is what? So I'm going to try to explain this as just efficiently as possible, just tell you exactly what to do, what to look for, etc. First step is focus on the denominators and go ahead and find the x values that would make this denominator equal to 0. Basically, what I do is take the opposite of what I see. That's how I think about it. That's a nice, easy way to think about it. If you see x minus 6, then x equals positive 6. Because if you plugged in positive 6 for x, you'd have 6 minus 6, which is 0. The idea is finding the x values that make the denominator equal to 0. So likewise, for the other factor x minus 2, you'd have x equals 2. The squared in the x minus 2 does not make a difference. Just focus on the factor and getting the x values from those factors. Now, we have x equals 6 and x equals 2. Now we ask ourselves, do either of these, 6 or 2, fit into this inequality? In other words, is 6 less than negative 1? Nope. Is 2 less than negative 1? Nope. So really, we actually don't even need to include these values, because if this function is only defined for x values less than negative 1, then having x equals 2 and 6 be not in the domain, they don't make a difference. Like, they're not in the interval for that piece of the piecewise function, so they're not going to cause a problem. Okay, so we don't include those. We move on to the next one and repeat the process. All right, so this one here, again, we have x equals 6 and x equals 2, it looks like. Again, just from these two denominator factors. 6 and 2, when plugged in, would make those denominators, would make that denominator equal to 0. So then we ask ourselves, is 6 between negative 1 and 5? It is not. We ask ourselves, is 2 in between negative 1 and 5? It is. So because 2 is in between negative 1 and 5, we now want to include the 2. Now we move on to the last one. The denominator, x minus 6, would give us x equals 6, and then the other piece, x plus 2, would give us x equals negative 2. Keep in mind, it's sort of the opposite of what we see in the factor. We ask ourselves, is 6 greater than or equal to 5? Yes, 6 is greater than 5, so it fits in this domain. Now, is negative 2 greater than or equal to 5? It is not. So we get rid of that. And now the only boxed x values we have are 2 and 6. So those are the only two x values that would eventually not be in the domain. Okay? That was number 15. Let's do number 16. They ask which of the following expression, write the following expression without absolute value symbols. So the approach here is we're going to drop the absolute value bars. When we do so, we could either have a positive outside the parentheses here, or we could have a negative. So we're trying to figure out, should we have a positive or should we have a negative when we drop the absolute value bars? That's all going to be dependent on this little domain interval they give us here. They say given that x is between 7 and 8. So my approach is this. Imagine you've picked a value between 7 and 8, say 7.5, and you've plugged that value in x here. And you ask yourself, what would that give us? What is 7.5 minus 7? Well, 7.5 minus 7 is 0.5, but more importantly, it's a positive 0.5. It's a positive, meaning that you can drop the absolute value bars and just leave the x plus, or sorry, oh my gosh, this is at x minus 7 the whole time? Jesus, I'm sorry. Anyway, you can drop the absolute value bars and leave x minus 7 as a positive expression. And that's it. So leave it as positive because 7.5 minus 7 was positive. Okay? Had we plugged in a value, say like 6, that would have made the inside of the absolute value bars negative, then we would have tacked on a negative. But again, the x values are between 7 and 8, so we couldn't plug in 6. Okay? So now we do the same thing with this. If we plug in 7.5 in place of x, we have 7.5 plus 6. That's a very positive value. So we can just leave the x plus 6 as a positive when we drop the absolute value bars. So now we can just simplify this. We can drop the we can drop the parentheses. And now, combine like terms. So we have x plus x, that's 2x. We have negative 7 plus 6, that is negative 1. 2x minus 1 is what we're looking for. And that's all there is to it. Okay, so it's the idea of if you drop the absolute value bars, you're going to have to either tack on a positive or negative based on whatever the domain interval is that they give you. Okay? Okay, that was number 16. We just had 2 more here. Number 17, they say, which of the following inequalities describes the value of x that are shown in orange? Okay. First thing to identify, in my opinion, is probably the center of this interval. And so this interval is ranging from negative 8 to positive 8. That's convenient. If it was not ranging from negative 8 to positive 8, if the numbers were a little more wacky or off-centered or whatever, what you can do always to find the middle of the 2 endpoints, to find the center of the interval, is add the 2 values together, add the 2 endpoints together, and divide it by 2. So in this case, we have 0 divided by 2, and that's why we still get the middle, the center of the interval, as 0. So if 0 is the center, we always want to see the absolute value of x minus the center. Likewise, or I guess like the next thing we look for is that inequality, or sorry, that absolute value should be less than or equal to whatever the radius of the interval is, or the half length of the interval is. So if the center is at 0, the radius is considered the half length of the interval. It's like the distance from the center to the outer boundary, the outer end point. So if we go out 8 to get from the center to the end point, then that radius is 8. And we want to see the radius on the outside of the inequality, or the other side of the inequality. So x minus c, where c was 0, that would just be x minus 0, which is just x. So really we should just see the absolute value of x is less than or equal to 8. That's option A. So find the center, find the center's value inside the absolute value bars, and then find the radius on the right side of the inequality. Okay. That was number 17. We're going to wrap up with number 18 here. They say some values of f and g are given in the table. What is the value of g divided by f of x at 7? So just a notation thing here. Don't worry about this x. That's more of a notation thing. So like them saying g over f of x like this is the same thing as g of x divided by f of x. It's the same exact thing. Don't let it confuse you. Let me simplify it even further and say this is the same thing as this, just g divided by f. So really I would just think about it as, what is g divided by f at x equals 7? So at x equals 7, we have a g value of 42. At x equals 7, we have an f value of 49. So 42 over 49 reduces to 6 over 7. If we divide 42 and 49 both by 7, we get 6/7. And that's it. All right. This has been 18 practice problems, 18 problems that you could potentially see on test 1. And so I'm just going to scroll through them. Maybe I start with the first one. Let me let my dog out first because he decided to start yapping. All right. Thanks so much for watching. Again, if you have any questions, email me. And if you want to see more review sessions like this in the future, this semester, I encourage you to become a member of the You Will Get an A membership. But regardless, if anyone has any questions, you can always email me. I'm always happy to help. Alright, I'm going to wrap this up. Thanks so much for watching. Again, as always, if you have any questions, let me know. I'll try to get a more like regular schedule for these 10-14 sessions. It's been kind of jumbled past week or so with these, but if you have any questions, as always, let me know. All right, bye-bye.